you put inside. I don't quite see how to cinch that one up, but you get that all of the relevant information is summarized on the boundary, and the rest is conditionally independent. All right, that leads us now to the data processing inequality. If X, Y, Z is Markov, then the mutual information between X and Y is greater than the mutual information between X and Z. In other words, data processing going from Y to Z, this is semicolon. Data processing does not increase the dependence. It may even decrease the dependence between X and Z. That's really encouraging because it means that you can that if you process the information, you can actually lose some information about X. But it also is encouraging in the sense that sometimes you have equality here, which means that you've thrown away the inessentials and still kept, that is, thrown away the data and Y that doesn't matter and kept the data that does matter, because you still have equality with X. And that would be the case in the coins example. You could throw away the actual outcomes of the coin flips for this Bernoulli theta process and just keep track of the number of heads. That gives you as much information about theta, the unknown. Whoa. What just happened? The tray, the disc tray came out. Got me. Yeah. Okay, let me quickly prove this and we'll take the break. Proof. The mutual information of X and Y and Z is, I'm going to expand it in two different ways. It won't be the last time. I of XZ plus the mutual information between X and Y given Z. That's the chain rule for mutual information. Now I'll drop down, leave space. This is also I of X and Y plus I of X and Z given Y. So those are two expressions for the dependence of X on the pair YZ. Now let's examine the terms. Here's one of the terms I wanted here. Here's another one of the terms I wanted here. What is I of xz given y? Anyone? Yeah? 0, right. It's 0 because they're conditionally independent given y by the assertion of Markovity. So this is 0. And who knows what this thing is, but it's always non-negative. And now you have the desired result. This quantity is equal to this quantity. This quantity is equal to this plus something non-negative. So this is greater than or equal to that, which is this result. All right, so let's take a 2-minute break. When we come back, we'll look at the notion of sufficient statistics and the implications here. Okay, homework gets turned in here. And homework set 2, if you haven't picked it up, you can pick it up here. Excuse me?
By the box, can we submit the homework at the box in Cracker?
Yes. When are you going to hand it in?
Today, sometime.
Sure. Yeah. There's a place, you know, you've seen the box?
Okay.
All right, good. Yeah.
I want to ask you a question.
Or you can give it directly to the graders. That is, the TAs or, you know, that student office right near mine. Yeah.
So we define entropy for a random variable, right?
Yeah.
But here we have this h of PE, but PE
Yeah.
is a number.
Yeah.
I don't understand this notation.
Okay, here it is. H of x is equal to minus summation P of x log P of x. Sometimes I write that as equal to H of P or H of P. In other words, H of x is really this function. So I can refer to what function it is by saying it's the probability mass function of x, or it's this probability mass function.
Okay, so this is just a different notation for this.
Right. Now, H of PE should really be written H of P 1 minus P, because it's a binary random variable, but it really only depends on this. So I write H of P equals minus P log P minus Q log Q. Well, 1 minus P log 1 minus P. Ooh. Good.
Okay.
Yeah.
One more question.
Yeah.
In the homework, we're supposed to show this.
Yeah.
How do we start? Intuitively, this makes sense. Oh, okay. And then the data processing code.
No, actually, if you've proved that H of G of some random variable Z less than or equal to H of Z. We proved that, or, you know, data processing, anything. Yeah, right. The entropy of a function of a random variable is less than the entropy of the random variable. And that's the reason is because we're amalgamating various probabilities.
Yeah. They are equal only if it's the bijection.
Only if knowledge of G will enable you to recover Z. Then you have equality.
Okay.
Sure.
So G is 1 to 1? Yeah.
Yeah. Here G is not 1 to 1. So you actually have strict.
We have till 5 o'clock to turn
Yeah,
Because I need to staple that.
right. Okay, good.
Have you determined when the midterm will be?
Yeah, normally it would be the 13th lecture, but I'm going to miss like the 8th and 9th, so right now I'm putting together a syllabus that either will have those taught by somebody else, or I will excise that material without damaging the course.
So 13th lecture is when it'll be?
No, but certainly after the 9th lecture. How soon do you need to know?
I have a wedding I have to be to, and I need to know if Thursday in February I need to be here.
Yeah, well, that's probably when the midterm will be.
Yeah.
So,
I mean, what it comes down to is whether or not I make the rehearsal dinner. You know, so
no, you got to make that, and that's the bachelor party and everything. Maybe. Yeah. I'll know probably by mid next week. Okay, great. Okay, so what we've argued is that all three definitions of Markovity are equivalent. X to Y to Z, Z to Y to X, or X and Z being conditionally independent given the middle term Y. They're all equivalent definitions. The last definition was the one that generalizes to high-dimensional processes. I've proved there the data processing inequality. Now let's look at a corollary of it. If Z is a function of Y, then I of XY, mutual information between X and Y, is greater than I of X, given G of Y. Some people would call this the data processing inequality because when you process data, Y, you often just calculate a function of it. But this is a special case where G is this degenerate function. That is, G is not a degenerate function, but the conditional distribution of Z given Y is degenerate. Its mass is either 1 or 0. All right. And here's another corollary. If X, Y, Z forms a Markov chain, then the mutual information between X and Y, given Z, is less than I of XY. What does that mean? We have X, Y, Z, and the dependence of X and Y is this mutual information. And if we are now given Z, that causes the dependence to be less. They're more closer to being independent than they were before. And these are just immediate consequences of that argument.